Welcome back to Physics through Computational Thinking. In this video, we are going to learn about Euler's method of solving ordinary differential equations. So let's go ahead and get started. Remember, when we were discussing about harmonic oscillator, simple harmonic oscillator, and then damped harmonic oscillator, and harmonic oscillator, we ran into equations which we could not solve analytically. In such a case, you'll have to resort to a computational technique to solve for a differential equation, such as Euler's method. So Euler's method is one of the simplest methods of solving differential equations or ordinary differential equations, and we are going to learn about the numerical method called Euler's method in this video. So let's go ahead and get started. Euler's method aims to solve a differential equation of the sort x dot t equal to f of xt. So let's consider this simple example. X dot t is f of xt, where f of xt can be any function. To give you a simple example, x dot of t can be simply some function of x and t, in this case only a function of x, let's say minus 2x. In order to solve this equation, the first thing that I want to do is I want to write this as dx over dt, and then I want to write this as equal to minus 2x. And then usually what I do is, when I'm solving this analytically, I'll bring everything of x on one side and t on the other side and go on. But when I want to do it numerically, what I want to do is I want to start from some initial position. Let's say I have got a time axis on the x-axis and I've got x of t on this axis, and to start with at t equal to t0, I know my initial value is over here, that is x at t equal to 0 is given to me as some value x0, which in this case is over here, this is x0. Now I want to find out what happens to x a time dt later. So in order to find that out, all I need to do is write dx as minus 2x dt, and I can go ahead and on this graph I can find my next point by calculating what is minus 2x dt. That means in time delta t, that is if this is time dt, I want to find out how much is dx, and dx is minus 2x dt. So if I calculate that dx, that is going to be some height, let's say is this much. So at time dt later, that is at t0 plus dt, my new point would have shifted over here, and I'll repeat that process. And at, let me call this point as t1, at t1 this is my value of x, which is x1, and then I'm going to go ahead and go to point t2. At point t2, which is again some dt distance away, I want to find out how much x has changed. So I will go ahead and calculate dx again at point t1, and for that I'll use, so dx2 is minus 2 x1 times dt1 or dt does not change, dt is always same. So when I calculate this quantity, I get dx2, and let's say this is my dx2, and if I know dx2, I can find out this and keep on doing that. And that process, what will end up happening is I'll generate a solution for my differential equation, some curve which is represented by this white line. So what I'm doing is I'm solving differential equation step by step for a small time dt at a time, and as a consequence I'm generating the entire solution. This is the essence of the Euler's method. Let's understand this method. Let's understand the systematics of this method. So in order to implement Euler's method, or what we do is we write first dx as fxt dt, where fxt is a derivative dx by dt. Now what we do is we take the time slice. Suppose we want to solve a differential equation from time t0 to tf, or some t initial to tf. So let me go ahead and do that. Let me take my time slice. This is t initial, which I will also call as t0, and let's say this is T final, which I also call as Tn, where n is number of intervals, time intervals in which I want to do the calculation. So what I'm going to do is I'm going to cut this graph into very thin time slices, all of equal size, like that, like that. Each of these time slices will have some width. This width I'm going to call as h, that is h is equal to Tn minus T0 or Tf minus Ti divided by n. So the total number of intervals I have over here is n intervals. The total number of time instance I have is n plus 1, T0 being the 0th time instance, and this being the nth time instance. Total n plus 1 time instances. Between that I have got n intervals, and I can also write this as Tf minus Ti, final time minus initial time, divided by the number of intervals. So h is my step size. I can also call h as step size. Once I've got my step size, I can go ahead, and once I've calculated my h like this, I can go ahead and write x0 as xi, and after that any x n plus 1 is simply calculated as f of xn comma tn times h. H is nothing but dt, or the step size, and I've evaluated the function at its previous value, at the previous point. So this determines my new xn, and similarly my new tn or tn plus 1 is simply tn plus h. Alright, so this is the essence of the Euler method. This is how the Euler method is implemented. So now we'll go ahead and implement, I'm sorry, this is the increment in, so let me correct this. This is the increment in, so xn plus 1 is xn plus the increment in x, which is the change in x. This is the delta x at that instant. So I'm adding to xn the change at that instant, that is the delta x, and that will generate me a solution. So my solution will start from some initial value over here, next instant will jump over here, and so on, depending on the derivatives. F is the derivative, as you would have noticed that this f is the derivative. So f is telling me the slope at this point. So what I'm doing really here is, at any given point I'm finding out what is the slope of the function. Once I know the slope of the function, I move dt distance along that slope, and that gives me the delta x. This is the dt along the slope, and that gives me the height. So that determines my new point, and so on. And when I join all these points through, it'll generate me a smooth curve. So that is the idea behind the Euler's method. So let's go ahead and learn how to implement it on a computer. In order to implement this on a computer, what we'll do is we'll use the for loop. Remember the structure of the for loop. For loop had 4 arguments inside the square brackets. The first argument was initialization, second was condition, third was increment, and fourth was body. We'll use the for loop to do this iterative procedure of implementing the Euler's method. Note that we discussed that for loop is less efficient compared to a table command, and we use for loop when decision for this instant or this iteration is based on what happened in the last iteration, or we need the information of the last iteration to determine the value of this iteration. That is when we use the for loop. While table is something that applies on an array, and something that we will try to apply on an array in one go, that is when we'll try to use the table command. So over here we need to know where the initial x was, where the last xn was in order to determine the next xn plus 1. Therefore, we are going to use the for loop. So let's go ahead and learn how to implement Euler's method using the for loop. For this purpose, let's go ahead and take this example x dot equal to minus 2x, and the initial condition is x at t equal to 0 is 1. First, let's go ahead and solve this equation analytically. So the equation that I want to solve is x dot is equal to minus 2x. Solving it analytically, I get dx equal to minus 2x dt, and I can write this as dx over 2x, or rather dx over x minus 2 dt. Integrating both sides, I get log x equals minus twice t, and I can write this as plus a constant, and I can write this as x equal to e to minus 2t times the constant log. When I take the exponential, e to the power c becomes a multiplicative constant, which I'm going to call a, and this is my solution. This is my solution for the equation. I need to determine what is a. To determine a, I'm going to use the initial condition. Initial condition given to me is x at t equal to 0 is 1. So that implies that a times e to the power minus 2 times 0 is 1, e to the power minus 0 is 1, therefore a is equal to 1. Therefore my solution is simply x equal to e to the power minus 2t. Good, now that we have found the analytical solution, we will use this result to compare with our numerical solution. So let's go ahead and implement this numerically using the for loop. So here's my function. So I'll define my function as a function f with two arguments, one argument being t, the other being x, and in order to define a function, I'll use an underscore so that Mathematica understands, or Wolfram language understands, that t is a variable, not a particular value, x is a variable, not a particular value, and I say f of tx is equal to minus 2x. In this case, let me remove the semicolon, execute it. So f of tx is defined as minus 2x. I can go ahead and give some value of t and x and find out whether this is working properly or not. It's clearly independent of t, and you can verify that. So that's my f of tx. Now I'm going to go ahead and define x initial. I'll call that as xi. So xi is 1 for me. Similarly, ti is 0. Let's assume that we're going to solve the equation from t equal to 0. So to some final time, let's say t equal to 10. So my final time tf is 10. Now h is going to be tf minus ti divided by n max. Let's go ahead and also define n max. N max is the number of steps that we want to use. Let's say we have to start with 20 steps. With 20 steps, let me go ahead and call n max over here. Let me go ahead and execute this statement. Notice that I have defined all of these things in a single cell. This is my initialization of the problem. This initialization of the problem, I'm going to define a single cell. I don't have to write separate lines. Just makes the code more compact, and it's easier to work with and read. So let me go ahead and execute this to find out what is my h. So n max has been defined with a capital M. So let me do that. There we go. So this gives me h equal to 1 by 2. All right, Mathematica is a symbolic language, so it will give you 1 by 2 rather than 0.5. We'll see what is the impact of that in a moment. So let me also go ahead and suppress it with a semicolon. So this is my initialization or definition of the problem. So let me go ahead and just mark it up. This is initialization. slash define Alright, let's go ahead now and define our for loop. But before I write for loop, I should decide how I want my solution to look like. What do I want my solution for? So what I really want is my solution to be of the form, it should be list of lists. So I should have the structure of the solution in the form t0 comma x0 so I want my solution to be in the form t0 comma x0 t1 comma x1 t2 comma x2 and so on. So this is how I want my solution to look like. So if I want my solution to look like, I'm going to call this as data list. Okay, this is my solution. So this is I'm going to call this data list. So I want to, all I know is that I know t0 and I know x0 and I know tf and I know the differential equation x dot equal to minus 2x, and I want to generate a set of points at each interval. So distance between t0 and t1 is h, distance between t1 and t2 is h, and so on. So I want to generate this set of point tn comma xn at each interval. In order to do that, I should go ahead and define my empty array data list. So let me go ahead and define this as empty array. Okay, now I want data list, I want to take this data list and I want to prepend to this data list, sorry, append to this data list or add to this data list the first value, that is the first value x previous and t previous. For that I need to define what is x previous and t previous. So x previous is simply xi and t previous is simply ti. So this is my previous step, which is what I already know, and to this I want to add t previous and x previous. So let's go ahead and execute that and see. So there we go, we get my the first element of data list as 0 1. So we can go ahead and check that out. So the first element of data list is 0 1, and that's all that is there. Now I want to go ahead and calculate the next step and next step and next step, and I want to do that using a for loop. So let me go ahead and at this point start writing my for loop. So I want my for loop to be have 4 things, and I'll enter each of the things in a different line. So first line is initialization, so I'll say let me use the counter n, so I'll start from n equal to 0 and I'll say that is my initialization, and all the arguments should be comma separated. So then I want n less than equal to n max, which is the number of steps I want to do. Rather, I should start from n equal to 1. So n less than equal to n max, and I want to increment n. To increment n, I will simply use n plus plus. And now here I want to write the body of the for loop. So this is the initialization part of the for loop. Notice the combination star and round bracket is used for commenting in Mathematica. So anything typed inside a pair of star and round bracket will be ignored. this is condition. The for loop is going to work as long as this condition holds. This is incrementing step, and then finally the body appears over here. So what we want to do in the body is we want to find x next and t next. So t next is t previous plus h, that's straightforward, and x next is x previous plus h times f evaluated at t previous comma x previous. Once I have that, so this is where the body starts. Let me mark this up as body. So the body is from here to the end. So this is my x previous, t x next and t next. Now what I want to do is I want to push this x next and t next inside the data list. So I'll say data list equal to append. Append is going to add the next point into the data list, and over here I'll say t previous, t next and x next. That is my append statement. This is going to add one more line, one more set of points to data list, and now I want to update x previous and t previous. Once this is done, x previous will become x next and t previous should become t next, so that we are preparing ourselves for the next round. Very well. So you see that my body contained multiple statements, and those statements were separated by semicolon. The arguments of the for loop, there are 4 arguments of the for loop: the initialization, condition, increment, and the body. Those 4 arguments are separated by comma. I pressed an enter after each comma so that all these lines are separated from each other, so that you can read more easily. Otherwise, pressing the enter is not required. I can go ahead and combine all of this in one line, will be perfectly fine. Will just becoming a nightmare for you to read and understand. So therefore, I am putting each one of these statements in a new line. So as a single argument of the for loop can contain multiple statements. Those statements are separated by a semicolon, and arguments of the for loop are separated by a comma. And this is a structure which is common across Mathematica. This is not particular to the for loop. This is pretty much true for any function. Arguments are separated by commas, and within a single argument you can have multiple statements separated by semicolons. The last argument, which doesn't contain the semicolon, usually is passed on as the value for that argument. In this case, all of these statements are suppressed by a semicolon, so the evaluation of this entire block is going to be null, but that doesn't matter to us because what we are interested in calculating is the data list. Okay, so looks like we are ready. So let's just quickly review what we have done and cross check if we have not missed anything. So to start from here, we initialized data list as empty. We started out initializing x previous and t previous as xi and ti, the initial points to start with. Then we appended to the data list the t previous and x previous values. Once we have done that, we came down to the for loop. We decided to run for loop from n equal to 1 to n max, because we have got n max steps. So every time we are going to increment n by 1, and in each step when we do that, we are going to calculate t previous as t previous plus h, increment time by 1 step, and calculate x next as x previous plus h times the derivative of the function at the previous point, and that gives me the delta x value, which is this. Adding it to x previous gives me x next. I want to insert x next and t next and x next into the data list, so I am using the append to append t next and x next into the data list. If we have not discussed append earlier, this is what append do. Let me quickly show it to you. if I start with a list 1 2 3 4 and I ask it to append 5 to this, the output will be a list in which 5 is added to the end. In the case that we are talking, we have got pairs of values like this. So we have got a list of lists. The inner list contains 2 values, let's say something like this, and to that we want to append something else. It doesn't really matter. Mathematica doesn't necessarily need same kinds of values in a list. It can take arbitrary expressions inside a list. That means all the elements of the list should not have the same properties. For example, in this case, this is my outer list from here to there. It has got 5 elements. First one is a pair, the second one is a pair. Sorry, 4 elements. First one is a pair, second one is a pair, and these are single numbers. To this I am appending 534. 534 is a 3 tuple. This 3 tuple will be appended as an independent element to the list, such as over here. So now this list has 5 elements. This is the first element, this is the second element, this is the third element, this is the fourth element, and this is the fifth element. Now this was an arbitrary example to just demonstrate to you what does append do. For our purposes, all elements are of the same variety. There are 2 tuples. The first element of the 2 tuple is time. The second element of the 2 tuple is the x variable, and we are appending them in pairs, such as over here. So my data list will be a list of 2 tuples. Okay, let's go ahead and execute this. So that has been executed. Now I want to see what is the outcome of this. So let me go ahead and print data list, and there we go. We got pairs of points. The nice thing about Mathematica here, Wolfram language here, is that it's going to calculate them as symbolic expressions or fractions rather than necessarily numbers. But there's a disadvantage of that. Usually such a process becomes slower. We'll see that in a moment. We'll compare that in a moment. But this is my data list, and you see at some point, since the solution, as we saw, was exponentially decaying function, at some point actually right over here it became 0, and then it always remained 0. Okay, that is quite accidental. Actually, we can go ahead and try something else now. We can go ahead and make maybe n equal to 100, and then initialize this again, and then run the for loop again, and then print the data list again, and there you go. You see a long list of numbers over here. Okay, this becomes very difficult to read, and that's what I was saying. And also actually it starts to take a lot of computational time. So there are 100 numbers over here. These fractions are small numbers, but they're much more difficult to read. So what we'll do is we'll make sure that this is done numerically. So to make that simply, what we'll do is we'll simply put a // n over here, so that h itself is evaluated numerically rather than as a exact expression. So h becomes 0.1. Now the moment h becomes 0.1, every time a decimal number enters in the calculation over here, and as a consequence all these numbers will get evaluated to numerical values, which will become much more readable. So let's go ahead and do that. So let's go ahead and execute this statement again, initialize this part again. If you don't remember, the data list has not been set to empty, to initialize, and running the for loop will simply add more and more values to the previous data list. So that is the reason why I need to run this set of statements again. That's why I'm pressing shift plus enter over here. Now at the for loop, when I run it again, I'm going to get this data list, and now you can see it's much more readable. At t equal to 0, I have x equal to 1, which is my initial condition. At t equal to 0.1, x is 0.8, 0.2 it's 0.64, and so on and so forth. It's dropping down, and very quickly at about 3 or 4 it becomes a very small number, dies out. This is what you expected for this equation. Remember, this equation was x dot equal to minus 2x, and the solution we found was x equal to e to the minus 2t. So it's exponentially decaying solution. For exponentially decaying solution, you expect x to become smaller and smaller, converging to 0, and that's exactly what's happening over here. That's what you expected. So let's go ahead and plot this and find out if this is exactly the solution that I wanted. Is it exponentially decaying as I wanted, or it is something that is decaying but not exactly the solution that I wanted. Okay, so what we're gonna do is we're gonna do a list plot. We'll enclose this inside a list plot. Okay, you can also do a postfix. So for example, you could do that. That does look like a a decaying function, but is it the solution that we are looking for? So we have to compare this with our solution. So let's go ahead and plot our solution. Our solution was e to the power minus 2t, and we want it from t equal to 0 to tf, which was tf was 10. So let me just put tf over here. This is tf, or rather ti to tf. That's my solution. Let me go ahead and put them on top of each other so that you can compare. And to do that, I will use the show command, and I'll say, for that I'll define them as something. So this I'll call this as data plot. So this is my data plot. I'll give them this is my solution plot. I'll put solution plot and data plot on this, show them together, and you see they're quite close but not right on top of each other. That's quite interesting. So we got really close to the solution that we expected. So this is my the dots are my computed value, and this is the solid curve is my analytical value, and they're very close to each other, but they don't quite overlap. The reason for that has to do with the fact that the step sizes are probably too large. H is 0.1, which is probably too large for this thing. I want to make h smaller, so maybe I want to make it 200. When I make it 200, h becomes 0.05. So let's go ahead and rerun it, rerun the for loop again, make the data plot again. Okay, it becomes more denser, make the solution plot and show them together, and that got a little bit better. They came closer. So which means that I need to make my h further smaller to get an even better agreement. So let me go ahead and do that. So let me make it 500. So that makes h 0.02, and let me go ahead and do this, execute this for loop, make the data plot, make the solution plot, and show them on top of each other. Now they're in almost perfect agreement. So now you see that step size is extremely important. If your step size is too large, you might get roughly the shape of the solution, but you'll not exactly get the solution. So you need to choose your h appropriately. At the same time, so you can say, I can go ahead and make h very, very small by choosing large number of steps. So for example, I can go ahead and make it 10,000. When I do make it 10,000, becomes very small, and I can go ahead and do this, and can produce a really dense plot, and I'll get a perfect solution. Okay, over here you see almost a perfect solution. In order to see the perfectness of that solution, I will join the points here. I want to actually remove the points, so I should do point size as that's the wrong option. I think I need to see what is the correct option. I think it's plot marker. plot markers as none should do that. There we go. So that's my, and let me maybe make the plot style as blue. Now I'll go ahead and put this on top of that, and you see they are right on top of each other. In fact, they're right on top of each other, and for very small h in this case, we see we have produced a perfect solution. But the cost of that is our data list is very long. If this is a more complicated function to evaluate, the time it's going to take is much larger. So therefore, it's not very beneficial to actually have such a small value of h or such a large number of step sizes. To make it more efficient, so we have to find a balance between the accuracy that we want and the number of steps to do the calculation that is required. For simple problems like this, it doesn't really matter. You can choose Nmax to be very large and h to be very small. But in order to optimize, we may probably want to decide to stick to some number between 500 or 1000. I thought 500 was pretty decent, so let's go back to 500 and do this again. And there we go. So 500, we see it's quite decent. The black and blue curves are sitting almost on top of each other, and the computational time involved is also very less. If you don't believe me, you can go ahead and we can go ahead and try this out. We can check the computation time. So let's say with 500 points, the computation time involved is in the for loop. So at the end of the for loop, I will apply timing to it and calculate the timing. So with 500 points, it took 0.0019 seconds, that is 0.002 seconds, to calculate 500 steps for this function. Now if I make it 10,000, that will be much larger than that. So let's go ahead and check that out. What happens when I make h very small? How does the computation time change? You see it's from 0.002 second, it has become 0.2 seconds, so the time became almost 100 times as much for doing this computation. So if you're solving a much more difficult and challenging problem, the time cost becomes 100 times more. That means that much more computation power you require, that much more hardware you require, and that is something that is not going to be feasible for all the problems that you're going to solve. So therefore, one has to think of optimizing the algorithm that you're using for the accuracy that you want. So in this case, the accuracy that we want, Nmax equal to 500, is quite decent, so we'll stick to that value. As we go along in this course, we'll explore more methods of advanced methods, improved methods, which will take the small value, reasonably large value of h, but still give me smaller accuracy. But let's go ahead and do a little bit more, learn how to make this code more efficiently. So let's quickly review what we have done. We initialize the problem by giving the x initial, t initial, t final, decided some value of Nmax, calculated h. Then we initialized data list, previous value of x, previous value of time, and then we appended x previous and t previous to data list, and then we executed the for loop. So this was our code, but I can actually make my code much more efficient and much more compact. So let's go ahead and see how to do that. So let me leave this part as it is, which is my definition part. What I'll do is I'll get rid of all of this by simply putting that inside the for loop over here. In fact, I don't even need n. Notice that I'm not using n anywhere inside the body of the for loop, n is just being used as a counter. So I can actually do that by simply, rather than using n for initialization, I can go ahead and initialize data list right over here as the previous value. So let me go ahead and define the previous value. So let me go ahead and the previous value is ti and xi. So this is my data list, and since I said I can enter multiple statements at the same argument, so in the initialization argument I'll enter multiple arguments by separating them with semicolons, and for that purpose I will also say x previous as xi. So this is my initialization of x previous, and t previous as ti. So all of this is initialization for me. That takes care of all these 4 lines, and I can go ahead and delete them. They're not required for me. Okay, great. So now my new initialization contains x previous, t previous, and data list initialization all together in one statement. I don't really require this either. All I need to do is check the length of data list. So I'll say the length of data list should be less than equal to n max plus 1. It already has the initial point t0 x0 or ti xi, and total number of instances that are going to have be inside the data list is n max plus 1, because n max is the number of steps. So then I don't need this increment n plus plus. In fact, I can copy this line I can go ahead and do this in the increment. Increment is always executed after the body, so I can remove these 2 lines and put them in the increment. There we go. So x previous equal to x next and t previous equal to t next becomes my increment, and my body becomes x calculation of x next and t next. And I can also go ahead and remove this, because this is an increment step. This is not really a calculation, I'm just incrementing my data list. So I can go ahead and also add that in the increment. So now my initialization contains initialization of data list and x previous and t previous. In the condition checking, I simply check whether my data list contains n max plus 1 instances or not. If it is less than that, continue to run. When the body is executed, it calculates x next and t next from previous, x previous and t previous. Once that has been calculated, I increment my x previous, t previous, and the data list. So I can organize my for loop in that particular way, and let's go ahead and check that this is actually doing the same job. So let me go ahead and start from this definition part. I'll go ahead and execute the for loop, make the data plot. It's the same data plot, of course, and the same result. I can go ahead and make my for loop even more compact. In fact, what I'll do is, rather than writing x previous and t previous separately, I will just call them as one item, that is previous, and simply go ahead and define it as a pair of 2 numbers, ti and xi. Once I define my previous like that, my updation also becomes previous is equal to the next. So let me write it as next, and this should be my next, and I can calculate next also in one go by saying next is equal to, next is a set of 2 items, so that is previous plus h and h times f acting on previous. So for that, I'll take f add previous. Note the use of add operator. F acting on previous is going to, remember that previous is a 2 tuple. That's what is intended. If previous is 1 comma 2, f added previous is gonna, or let me call it g added previous will be g of 1 2. What we want to do is, we want to take our function f and apply it to the arguments 1 and 2, and that will evaluate to some number. Alright, so What is this statement doing is it's calculating. I don't need this statement anymore now. So you see my for loop becomes much more compact now. I'm calculating the next point equal to previous point plus the change in the previous point or the increment in the previous point. So previous point is a list of 2 items. To that I'm adding another list of 2 items, and in Wolfram language of Mathematica the 2 lists can be added one item by item. Therefore each will be added to the first component of previous, which is the time value, and each times f applied to previous will be calculated and added to the second argument of previous, thus giving me next. And once I obtain next, in the increment part I'm going to set previous equal to next and append to data list next, and that makes my for loop very compact. So let me go ahead and initialize this again, run the for loop again, and calculate this again, and you see the same result. So it's doing the intended task. And so what we have accomplished by doing this is I made my code much more compact. Notice that I had to scroll back and forth, up and down again and again to see my code before, but now my entire code fits in one line. We can in fact go ahead and make this code even more compact, and I'll make a few more lines, but we'll take this up in the next time when we go ahead and improve our Euler's method to Runge-Kutta second order or improved Euler method. So we'll see you next time.